In R2, the chain rule applies when, say, a function y depends on u, but u is a function of x, right? It applies to compositions. And in first semester calculus, you would have seen that dy dx for a structure like this is expressed as dy du times du dx. To determine how y changes as x changes, we first determine how y changes when u changes, and then multiply that by how u changes when x changes. In R3, as you might guess, it's a little more complicated. Suppose we have an output z that depends on both x and y, but x and y both in turn depend on t. We have two kind of branches here, right? I've got z branching off to x and then t, and then z branching off to y and then t. So let's look at these branches kind of individually. To consider a derivative of z with respect to x, we need to consider it as a partial derivative because z depends on both x and y. And so what we're going to do is we're going to construct an expression that looks kind of like this, dy dx equals dy du times du dx. First, though, we're going to consider the partial of z with respect to x. Okay, so that's a partial with the kind of curly d's, right? Then, when we consider the derivative of x with respect to t, x itself has only that one input variable of t. You see, it doesn't branch. Therefore, it's the derivative of x with respect to t with the Latin d that you first saw when you saw derivatives. Likewise, when we look at the other branch, where z depends on y and that depends on t, because z depends on both x and y, the partial, or the derivative of z with respect to y is the partial of z with respect to y. But then because y depends only on t, it's the derivative of y with respect to t with the Latin d. Now, as with differentials, the change in z is a combination of the change in x and the change in y. And so dz dt, now these are Latin d's because z ultimately depends only on one variable t, right? I mean, t informs x and y inform z, but there's only one input variable, and that's t. So dz dt is equal to the partial of z with respect to x times the derivative of x with respect to t, plus the partial of z with respect to y times the derivative of y with respect to t. That's our derivative of z with respect to t, and it's really kind of like a total differential in that we're adding a change with respect to x to a change with respect to y. Let's jump to an example here. Find dz dt if z is equal to x minus y over x plus 2y, x is equal to e to the pi t, and y is equal to e to the negative pi t. Before we get started, I'll say it is possible to substitute x and y in the expression that defines z by e to the pi t and e to the negative pi t respectively, and then just use the quotient rule. But we're not going to do that. We're using the chain rule. For the chain rule, we need some parts. We need the partial of z with respect to x, the partial of z with respect to y, the derivative of x with respect to t, and the derivative of y with respect to t. Now, folks, you've seen the formula. You know how to find derivatives, partial and full. And so I'd like for you to go ahead and pause the video and work this one out. Well, I've done this using colors, and I haven't finished because I didn't want it to be too overwhelming here. But the partial of z with respect to x is going to use the quotient rule. And we have 1 times the quantity of x plus 2y minus the quantity of x minus y times 1 divided by x plus 2y, the quantity squared. That simplifies to 3y over x plus 2y, the quantity squared. For the partial of z with respect to y, we again use the quotient rule, and y is our variable of interest, x is a constant, so when we differentiate, of course, it's with respect to y. -1 times the quantity of x plus 2y minus 2 times the quantity of x minus y is equal to x plus 2y, the quantity squared, which simplifies to -3x divided by x plus 2y, the quantity squared. Partial of d with respect to, partial of x with respect to t just gives us a coefficient of pi in front of e to the pi t. Partial of y with respect to t also gives us a coefficient, but this time negative pi times e to the negative pi t. There are a lot of letters running around here, folks. Bear with me, please. I want to put this together with you, though. So we can say that dz dt is equal to 3y over the quantity of x plus 2y squared times pi e to the pi t plus, because we have negative times negative, 3x over x plus 2y, the quantity squared, times pi e to the negative pi t. I'm not going to leave this as my final answer. I think you might see stuff like this in the textbook. I'm going to say that it is preferable to express dz dt in terms only of t. For this, we're going to use our definitions that we have. X is equal to e to the pi t, y is equal to e to the negative pi t. We're going to substitute those wherever we see x and y. dz dt will then become 3e to the negative pi t times pi e to the pi t plus, that was replacing, in place of y. Now we're going to replace in place of x in the numerator. So plus 3e to the pi t times pi e to the negative pi t divided by, now we're going to replace x by e to the pi t and y by e to the negative pi t in the denominator. So we have e to the pi t plus 2e to the negative pi t, the quantity squared. You may notice that some factors divide out in the numerator, right? We have two instances of e to the pi t times e to the negative pi t. In both of those cases, there's a factor of 3 and a factor of pi. And so dz dt actually simplifies kind of nicely to 6 pi divided by the quantity of e to the pi t plus 2e to the negative pi t, whole denominator squared. Now, regarding simplified forms of final answers, you see that we have an e to the negative pi t in the denominator. Generally, we say no negative exponents, except with e. I like to imagine that a mathematical society one day got together and they had a vote and they said, yeah, we'll let e do it. Also scientific notation, but everywhere else, no negative exponents.